Okay, welcome to Biostats 347, and today we're going to cover the how-tos of an ANOVA. And before we do an ANOVA, there's a few things we need to check. And one of the things you have to understand is the design of your study. So you often gather data and ask somebody what to do, and they'll say an ANOVA. But then you have to ask yourself, how is my design structured? Is there repeated measures? Is there any nesting? This lecture is strictly for simple one-way ANOVA. So single treatment with various levels and a continuous response variable. So before you get started, the things you should check for are understand your study, do a Bartlett's test. The Bartlett's test will tell you if you got homogeneity or variance. The good thing is that ANOVA is fairly robust, but it is good to check and understand that you may have limits to what you infer. And it may be so severe that you can't do a ANOVA. But we can figure that out afterwards as well. Next thing you need to understand is if you're doing a hypothesis or a model. So are you only just asking if your treatment has an effect, or do you actually want to understand the effect size? And I will push you to approach your questions as modeling questions, because understanding the effect size really gets at the core of what's going on in your system. You should understand if you're doing a one-tailed or two-tailed test. So do you expect things to get taller with your treatments, or shorter or slower? And then any a priori questions. So if you remember in ANOVA, you have a continuous response variables in several groups. You may want to know ask ahead of time, how your groups are different from each other. Because the limits of ANOVA, if you remember, is if you just do a standard hypothesis test, is you're only testing if your treatment has an effect. You won't know what the difference is, if there are any differences between your groups. All right, so for this, I created a simulated data set. And so let's run through that real quick. So if you turn your attention to the screen, we are going to create groups A, B, C, D from random normal distribution. So we could probably guess how a Bartlett's test may turn out. We're going to have a balanced design, so samples of 50. And then for means, I'm going to pick basically two things. A and B are going to be very similar, and then C and D are going to be very similar means, I should say. And then A and B together are very different from C and D. So we'll see how that plays out in the test. And you will get different results because we're generating this data ourselves. So you will generate data and compare it to mine, and you may get slightly different results. Okay, so we'll quick run that. So A, B, C, D. And what we're going to do is, as data frame forces these sort of disparate vectors, so A, B, C, D are these different vectors, we're going to force them into the same data frame. A, B, and then C bind A, B, C, D, what that does is it puts them all together, and then we take that group and turn it into So we can just look at E by typing in E. And so we have A, B, C, D going across. So this would be wide format. So most of the time you want to do your ANOVA in long format. So we need to convert this wide format with groups going across like this. What we want to do is put the data on top and have a single response column and then another indicator column which would indicate what group they are, A, B, C, or D. Okay, so what we can do is stack. So let's do that. So we've stacked them. And if we type in F to take a look, okay. So now you can see our data is in long format. So we've taken this wide format, put all these numbers on top of each other, and since we didn't name these variables anything, our default column headers are values, and IND stands for indicator. So this is your indicator to indicate what group they belong to. Okay. And again, since this is randomly generated, your numbers will be slightly different than my numbers. All right. So we can look at the names and see that it's just values and indicator, and I don't necessarily like that. So we're going to change the names to growth and group. So we're going to make up some experiment that, say, looks at fertilizer in 4 different groups and look at the growth. And that's how we measure these things. And that's what those numbers represent. Hypothetical data set. All right. So the way to do that is with names, and our data set that we stacked was called F, so names F, and then the new names here, growth and group. So now if we put in names F, I hope that changes to growth and group. All right, you can see that down below. All right, so we're good to go. Now we have a data set we can mess with. How do we proceed? All right, the first thing we want to do is check for equality of variance between groups, also called heteroscedasticity or homoscedasticity if they're the same. And that's just Bartlett test. So we want to go Bartlett.test. And we have the variable we're measuring, which is growth, and tilde, and group. And we need to indicate our data. So here it's F. So tilde means as distributed by. So we're looking at growth as distributed by group. Okay. So we'll look at this test. Bartlett's test, and is the variance equal? With 3 degrees of freedom, the P is significant, which means that our variances are not the same. Well, that's because if we look at how we define our standard deviation, it was, we made them pretty tight with 2 and 3, but notice they are different with very large sample sizes, 50. So these are different, so that doesn't surprise us, but we're gonna just go ahead and move on and do the ANOVA anyway. All right, so let's do an ANOVA. But the first type of ANOVA we'll do is just a classic ANOVA. And what I mean by that is we're going to do a source table that you'll see in publications. And remember, the source table, ANOVA is analysis of variance, and it partitions the variance into various sources. And the sources are the treatment, the residuals, and the total. Okay. So if we want a table like that, here's what we do, right? So it's just AOV. It's not ANOVA, it's AOV, analysis of variance, right? So it's AOV, but let's call our analysis something, because we can, once we make our analysis an object, we can do things with that object. Okay? So let's call it my AOV. And what we'll do, we'll set it up. So we'll do AOV, and we want to do growth by group. So it's the same thing as the Bartlett test. Data equal F. Run that. All goes well, nothing happens, okay? So you can see in the R console that nothing's happened. It's just a return cursor. All right, so if you want to get results, you can just type in my AOV, but it gives you incomplete results. What you need is summary. We want a summary of my AOV. What does that tell us? All right, so again, your results are going to be slightly different, but hopefully the generalizations are the same. All right, so here's your source table. It gives you group, okay, and residuals are your two sources of variation. The third one would be the total. Okay. For your degrees of freedom, you have 3 and 196. And remember, to get the total, you just add those. So your total degrees of freedom in your experiment would be 199, right? That's 1 minus the total, right? All right, and then 3 degrees of freedom for your group, which is 1 minus the number of groups. Here's your sums of squares, okay? Remember, to get your total sums of squares, you add, okay? Your mean squares are the sums of squares divided by the degrees of freedom. Here's your F, okay? So here's your F statistic, and you would compare that to the critical F for 3, 196 degrees of freedom. Okay, and that's statistically significant. So this is 2 times 10 to the negative 16th. So that is significant, smaller than 1 with 1 significant place. All right, so you would reject the null, okay? And now you have evidence that there's group differences. Again, we don't know what those differences are. If it is A is different than B, B then C, D then E, or A and B, we don't know. All right, so moving on. What we want to do is make sure, so the question was, you know, when we did our Bartlett's test, it ended up that we had homogeneity or heterogeneity of variances because our Bartlett's test was significant. So then the question is, what does this mean for our analysis? The wonderful thing about R is that you can look and do a postmortem test. So the postmortem test is what we call when you do a test to make sure it was a good test. All right, so let's plot my AOV. And what you have to do, and I hope this works on a Mac, I'm working in Windows, you get this, it looks like the circle of death, but if you click, you should get a graph. Okay, so here's your residuals versus your fitted values for your model. Okay, and what you're looking for, here's the groups is, and you can see now the heterogeneity variance more or less. Okay, so A and B, not as variable as C and D, but what you're looking for is more or less to eyeball that the number of residuals above and below are about the same, and this red line going across is straight. Notice that it's waiting for something. If you click again, it forwards you to the next plot. So here's a QQ plot. And what this is looking at to see if your residuals are normal, that's one of the assumptions of ANOVA, is that for the residuals about for any group mean, right? For group A, if this is your mean, that your residuals, your observations are normally distributed about that mean. And if they are, ideally, everything will line up on the QQ plot line, right? And you can see the majority of points do, and there's a little bit of wonkiness on the high end, right? And there was a little bit of wonkiness on the low end. That indicates that there may be some numbers that are pooling on your data and maybe affecting your results. Excuse me. For scale and location, what that's indicating, so your standardized residuals, everything's standardized to 0. What you're looking for is something like that first, the residuals versus fitted. And again, you're looking for more or less a straight line. This is bent. It's bent too much. I don't think so. I'd still move forward with this. And here's leverage. So leverage is how much a point affects your results, any one point. And what you hope for is these things are normally distributed. So you look for clusters about the red line. Your red line should be on 0. And then they should thin out at the extremes, which you see. And then some of these points, in my case, 105 and 104 are look like they might be extreme points, as well as 165. So the question is, what do you do with those? So since I created these data, I know these are good data. And so I leave them in, but if this was your study, I might go back and make sure that these are legitimate points, okay? So you click through those and you can't save them as using like that. What you can do is you can actually change the graphing parameters. To do that, we use this function par, and we're going to create an output of our model diagnostics that we'll be able to use in a report or a thesis or a dissertation, whatever you're doing, and just paste it in there from R. So what we did was we're going to create a 2x2 matrix of plots, and then what we'll do is we'll rerun plot. So I'm going to plot my AOV, and it throws all up there. And now you can take this and plot that into a report. It's pretty handy. And those are your 4 diagnostic charts. All right. When you use PAR and change your graphing parameters, that's now part of R. And if you don't remember how you did that, do what I do and go back and always fix that. So I just hit my up arrow, and then I change my 2x2 to a 1x1. And the reason why I do that is, if you forget, it'll always want to plot any plot in a 2x2 matrix of plots. And if you only have one plot, it'll stick one tiny plot in the corner and leave the rest blank. and then you're stuck. This large margins and this plot up in the corner. So set your graphing parameters back. Okay. And then you can close that, and now you're good to go. All right. Moving on. All right, so let's say you are interested in ANOVA as a linear model. In this case, you're really interested in the effect size of your model rather than just saying, is my model significant, statistically significant? So I'm going to show you three things. One is the AOV, a linear model, and then a generalized linear model, and they will each give you different things. So a linear model makes the assumption that the errors are normal. So, and that's about it. And to run a linear model, it's just LM. So we'll do my LM. Let's clear this. So we have my LM. And what did we want to do? So LM is the function, linear model. Okay? And that just means that what goes into your response is just a linear combination of your predictors. Okay? And we'll do growth. Again. Okay. Comma, and then data equal. And if you run that, nothing happens. It's awesome. That's what it's supposed to do. All right, so again, you'll want to do a summary. And I prefer running the model and then doing the summary. You can skip calling your model an object and just nest the linear model into your summary statement. So from here, I could just write LM and right above and just do it one step. I like doing 2 steps. So we'll do summary, my LM. Okay. All right, so we get much different, we don't get a source table like we did doing AOV, although it's doing exactly the same thing. All right, let me break this down for you. Here's the linear models. This is what it ran. Most of the time I don't pay attention to the residuals. I'm most interested in this part, okay? What linear model does for you is it takes the lowest ranked, and it could be alphabetical, usually it's alphabetical, okay? So we had groups A, B, C, D, so it picks A to be the baseline, okay? And what it does is, the first thing is the intercept. So that is your baseline. So if you remember, we did a random draw from a mean of 10, okay? So the fact that we got 10 is not surprising. Okay, so that's our mean of group A. Here's our standard error. So I think it was 2. And so if you took 2 and divide it by the square root of 50, you should get about 3.982. This t value represents the mean, and if it's different from 0, and that's the p-value. So the fact that your baseline is statistically significant should not be that interesting, okay? Because that's just asking if your group isn't 0. So if you standardize this, all your data to 0, maybe you would be surprised that something is not 0. But here, the fact that your intercept is not 0, that's not a big deal. All right, these other numbers, group B, group C, and group D. These numbers represent the difference between that group and your baseline. So group B, our estimates that it is 0.8949 units larger than group A, which is about right because remember we did a draw of 11. And so you would add 0.8949 to 10.04, and that would tell you the average of B. Okay, so you add those together. And comparing group A to group B, that's what this t value represents. So this t value represents group B compared to group A in an orthogonal contrast. And it's not statistically significant. Again, your results might be slightly different, but remember, we made a draw from a mean of 10 and a mean from a draw 11, and we put on some standard deviations that made them overlap. So I'm not surprised at all that we don't have significant differences there. Groups C and D, if I remember correctly, we made it 20 and 21 maybe, or 19 and 20. I could go back and check really quickly. It was our norm 20 and 21. So that's pretty spot on. If you were to add these together, it would be 19.38, okay, pretty close to 20. And then 10 and 10 is 20. And there's some remaining over, we expect 21, and it's really close to 21. All right, so those are the estimates. So you would add, to get the average of group C, you add this coefficient to this baseline. And if you remember, I said you use these when you're interested in the effect size. So 9 is the effect size. So if A was our baseline, okay, we would have increased our units by 9 by being in group C, okay? And that is statistically significant. Same with group D. So these p-values are always compared to the baseline, okay? They're not compared to each other, which you'd have to do something else. All right, you get some more output compared to the AOV. So it also gives you multiple R squared and adjusted R squared, okay? So R squared is how much does our model count for the variation in our response variable. So the difference between 0.75 and 0.748 is how much the null model made up. So the multiple R squared includes variation that is included just by fitting an intercept. So that's slightly inflated. What we are looking at is the adjusted R squared, which is when you already account for what's taken up by the intercept, how much more variation does your model account for? In this case, it's about 75%. So depending on your project, that might be good news or bad news. If it's ecology, it's probably good news. All right, your F statistic, okay, which is the overall model. So this is 198.3 on 3 and 196 degrees of freedom. That should sound familiar because this output, the F statistic and this p-value are for the overall model, which we fit with AOV. So you can get an overall statistic with a linear model and some extra information as well. So again, the first thing you need to ask is, whether you choose AOV or LM is, what is your question, right? Are you interested in all the extras, the buzzes and whistles? Or just testing your hypothesis? All right. So an important caveat to this is maybe A, B, C, D, and A is chosen as your baseline. If you want to change that, so if you have a different baseline than what's listed there, let me just pull this up. Okay. So let's do this. So we're going to use a function called relevel. And what relevel does is if you want a different group to serve as your baseline, it'll do that. So let's say like we used A, B, C, D, but D's our control. And that we want to be as our baseline. So we use relevel. And it's pretty straightforward. So you use relevel, and we want, we used F, and it was growth. And you just say reference. So what it's doing is it's going to go to the vector. So not growth, we want group. Okay. We want reference to be D. Okay. Let's hope this works. Let's see. All right, so relevel worked. So you put in what vector you're interested in reorganizing, and then you tell it which group to be your reference. And you see over here, what it did was it now does DABC. And the question is, if I was to run ANOVA, what happens? All right, so unless you tell it that your data's been reorganized, it'll go back and do the same thing. So my guess is when you do relevel, you have to call it a new, create a new data set. So you would do like G. If this doesn't work, I'll have to come back and give you an update. All right, so let's relevel, and then we'll do, let's pull up my LM. And in this case, we're going to do data equals G. All right, object growth not found. So what if we did if this doesn't work? I have no idea. Nope. All right, I'll have to come back. I knew that's how you reorganized your groups, and usually it has worked for me, but I guess not in this case. All right, moving on, and I lost my place here. So, by the way, an awesome thing about using, in fact, this is handy, using a script and not just working from console. I'm doing something with ANOVA, and I lost my place. If I know it contains ANOVA, I can just do a search. So I just do a Control F, and that finds the next, and look, there it is. All right. So, let's do a generalized linear model. So a linear model, one of the assumptions is that your residuals are normal. In a generalized linear model, your residuals can be many different distributions. I'm not sure how many, but it can use it for all sorts of analysis. Poisson, logistic, and normal. I know there's many more, but those are the three of my go-tos. So since the residuals can be different, you have to tell it what those distributions are. So let's do our third approach to an ANOVA and see what we get. All right, so we're going to do my GLM, my generalized linear model. So if you remember, LM assumes normal errors. If we generalize that, then we relax the assumption about the errors. So we can do my GLM, and the code is, it's the same thing. Your response by your grouping factor. So we're going to have growth, tilde, and then it's group, data equal F. And then we need to add in family equals. And what family is indicating is the family of errors, the distribution. So R doesn't call normal, it calls normal errors Gaussian. So, and you put that in quotes, okay, since it's a string of characters. All right, let's see if this runs. Could not function. No, that's because I didn't call. The function is at my GLM, my object is called my GLM. So again, my GLM is just an object. You can call it whatever you want. It's GLM, your response by your factor. You indicate the group, and then what are the distribution of residuals expected to be. So this will be our go-to code for pretty much the rest of the semester. Since we can fit Poisson and logistic or binomial errors in here. And the nice thing about GLM is this doesn't have to be a factor. So we could have normal or continuous data. We could have group data, binary data. It fits a number of data types. That's why it's called generalized, right? So it's our go-to code for the rest of the semester. So let's do a control R to send it over to R. Again, nothing happens. We do summary, my GLM. So we're going to get output that is very much like LM. So we're going to get output that's like a linear model, right? It's going to look just like a linear model, but it leaves out stuff, but gives us stuff. So generalized linear models use maximum likelihood and it assumes that you're asking different questions from just a hypothesis test. So you get, with the intercept being your baseline group A, and then all those differences between your groups, and then the statistical significance. What it gives you is the deviance and the residual deviance. And what you want to know is how much reduction in deviance is there. And the smaller, the better. Okay, so now it's almost like the flip of R squared. So deviance is the deviation from fitted, right? So the smaller, the better. Okay, so null deviance, just fitting the intercept is 6,269.9, and the residual deviance, and now you have a variable, so you lose degrees of freedom, but it's much smaller. So it's 1,553.6. Okay, and the AIC, the Ikaiki Information Criterion Number, is 987.58. Okay, that by itself does not mean anything, but we can compare this model. Remember, if it was growth and we looked at different fertilizers, we can compare this to a model looked at genotype, or even just an intercept-only model to see if this works better than an intercept-only model. All right, and doesn't give you R squared. So it depends on your question. Are you interested in how much a predictor variable explains your response variable? Use an LM. If you just hypothesis testing, use an ANOVA, the AOV function. And if you are comparing models and have multiple models, I would go with the GLM, okay? Because the GLM, the generalized linear model approach, gives you the least amount of information for a particular model, but allows you to compare different models. All right, what else do I have going on here? The likelihood ratio test, there's 2 of those. And so likelihood ratio test allows you to compare 2 different models. And if you're doing a one-way ANOVA with just one treatment with different levels, right? So our treatment was, what do we say, fertilizer amount. We had A, B, C, D. We really don't have too many models. We have an intercept-only model, and we have a model with that treatment. And we can test that. I just used it a few minutes ago, in fact, on a project, and I think I have it. I just sent the code to somebody. Let's try it. Why not? All right. LR test. Not very creative, but that's useful when you can't remember the name of the test. All right, so our model was called what? My GLM. So let's create another null model called my null. Okay. And it'll be GLM again, and it'll be growth again, tilde 1. So when you put tilde 1, what you're doing is essentially fitting an intercept. Okay. And we're going to go tilde 1, data equal F. I think that's all I need. Okay. If you leave out, by the way, for a GLM, let's add it because it's good practice. For a GLM, the default is normal errors. So if you leave out the family statement, if you leave out the family statement, it'll assume normally distributed errors, but that's not always a great thing to leave out, because if you get used to it and you're using like a Poisson regression or doing logistic, you'll run the wrong model. So it's always good just throw it in, just good practice. So let's do summary my null. All right, and so the AIC is 1,260.6, and the ARC with our treatment was 987. And if you remember, if the difference was 2, they'd be pretty close. If the difference is 4, there's more evidence. We're getting close to getting rid of the intercept. If it's greater than 7, then we can pretty much ignore the difference. Here, the difference between the intercept only and our model looks to be about 73 AIC units. So there's significant support for our model with our variables, right? The smaller the AIC, the better. And the intercept only model isn't even close. But let's run a likelihood ratio test just to confirm. So what we do is LR test, and we're gonna do my GLM, my null. Did it not work? LR test. That should have worked. I'm not sure why it didn't. I'm going to pause and step away and then. Okay. The problem before was LR test is in a package called LM test. So linear model test actually is a great little package. There's a whole bunch of things that gives you p-values. So I ran install packages and in quotes LM tests. Took about 10 seconds to download. You pull it up using LM test, and then I ran the LR test, the likelihood ratio test, my GLM versus my null. And so you get model 1, model 2, the degrees of freedom in each model, which is handy to see. And it compares the reduction in deviance to a chi-square distribution. And if it's statistically significant, that means your more complex model. Here it's the one with the treatment, okay? The less complex one is the null model. So here the statistical significance indicates that our complex model significantly decreases the deviance. So that's good news, right? Because we told it to do that. So it's nice to see it as well. All right. And then the last thing I'll show you are post-hoc tests. So post-hoc test, if you remember, if you do a source table, and even with our linear models and our GLMs, we don't know which groups are different from which. If you do a linear model, you can look at the baseline. If you have a baseline, maybe you don't have a baseline. So if this wasn't levels of fertilizer, but let's say we had 4 different fertilizers that we want to know which one was best, we wouldn't have a baseline, okay? So post-hoc tests can address things like this. And I have a lecture on multiple comparisons that you might want to refer to, but I'll show you how to do post-hoc tests right now. Super easy, okay? So there's many different post-hoc tests out there. There's Fisher's LSD, least significant difference. There's Tukey's, Bonferroni. The go-to, my go-to is Tukey's, okay? HSD on a significant difference. And in R, it's super easy. And all you do is type in Tukey with a capital T. Tukey, HSD, all caps, and then the name of your ANOVA. And it's important that you did it as an ANOVA. Okay, so if it is a GLM or an LM, this will not work. So I think we called it my AOV. Okay. And so you do an ANOVA. And remember, if you do a post-hoc test, you can only do if your overall ANOVA is statistically significant. Here it was, so we can do a Tukey's test. If it wasn't, we should not do a Tukey's test. So if you remember, our F test for the entire model was statistically significant, so we move forward with Tukey's test. Okay, here's what we get. Okay, here's groups. A versus B, C versus A, D versus A, C versus B. And if you remember why we do this instead of just doing t-tests is that we inflate our type 1 errors. So Tukey's HSD is a way to avoid making those errors. Okay, and so here's the mean difference, and it looks a lot like what we told R to do, which is nice. And then here's the adjusted p-values. So A and B are not statistically significant with a post-hoc test, but C and A are, D and A are, D and A, C and B, D and B, and not D and C, which is kind of how we set things up. So this worked out kind of exactly as we expected. I think the last thing I wanted to do was the type of plot you would like to do. And the best type of plot for when you have grouped variables on your X and continuous response on your Y is a box plot. So a box plot's pretty easy. The code is box plot. And it's the same sort of code as what we've been doing. So we have box plot, and we want growth as a function of group. And all goes well. If I could spell correctly. And indicate the group. There we go. So here's our plot. It's not very pretty, so we might want to change our X and our Y labels. And if these groups have names, we could add names. So my battery's running low, and I'll try and do this very quickly. So if we want to change the X label, it's X lab. Type for fertilizer type. And then our Y label, just do with Y lab, and let's say that's growth centimeters per day, whatever. All right, and then the other thing I think would be nice is if we add in names. So we're saying here it's fertilizer type. Okay, so let's do C, names, equals, and we're going to create a vector of names, so we need 4. And it's closed in parentheses. I like to create that skeleton, so C, and then add open and close parentheses, and then 4 names, so we need something in parentheses, comma, 2, comma, 3, 2, 3, 4, commas between each, and we'll say So that pretties it up. Very nice. I like that. Couldn't publish it because it's fake data. Anyway, um, there's how you do ANOVA. I hope this was helpful, and I don't know what's next on the agenda. Multiple factor ANOVA. So next one will be slightly more complicated, and we'll deal with AIC and how to sort through models. That's it. All right, and my battery's dead. Look at that.